Okay, so I promised today to introduce the transformer architecture, finally. And what I want to do before I actually do that is tell you a little bit about prediction of next elements in a sequence, some kind of classical stuff. So if you remember, the task of something like a transformer is to produce sequences of elements from some set of tokens from sequences of elements. So ordered lists of tokens from ordered lists of tokens. And the basic problem the basic way that this is modeled is actually as just a next token prediction. So the idea is, and I'm going to kind of introduce some terminology as well and some notation, but you have some set that I'll call T, which is a set of tokens, a finite set of tokens. And you can think of these as words or letters in some alphabet. It's a set of tokens. And now, so T is a set of tokens. And now the task is beginning with an ordered sequence of elements of T. Predict the next token in the sequence. So this is the basic task that a transformer performs, at least the version of a transformer, well, the version of the task that I'm going to talk about. So one example that you might have in mind is, okay, again, sort of lying and thinking of tokens as, say, words in the English language. You might have the sentence or the list of words, the water of Walden Pond is. And your task is to predict what the next word is. Okay, so in this example, this is what would be called the history or the context. And maybe I'll denote it as H. And your task is to predict the next word. And the idea is that this history is some kind of sequence of words in a set of tokens. And this is the next word, which is also in your set. Okay, so if you're thinking about how you might learn how to do this, some kind of first naive pass at learning how to do this, if you had some huge corpus of sequences, like we do in the English language, is to try to maximize the probability of W given the history of H within your corpus. So the naive idea, so here's the task naive version. So to maximize the probability of W given on H, on having seen H. And you're maximizing it over words in your set of tokens. Okay, so this is for fixed H. Okay, and one thing you might think to do is to try to approximate this conditional probability by looking at your whole corpus. Every time you see the water of Walden Pond is, you count that, and then you just look at what follows and you count those. And this is some kind of empirical approximation to this probability. So the idea is, so if you have given a lot of data of sentences, sequences in this language. Count sort of the number of times you see H. Sorry. So for each, let me see it this way. For each token in your set, and this fixed H history in your set. Now the number of appearances of H, comma WI, divide by the total number of appearances of H. And this is some kind of nice approximation for the conditional probability of W given, sorry, WI given H. And now you just want to pick the one that is maximized. So, okay. So what's the problem with this? You might not have any appearances of the water of Walden Pond is in your corpus. And in fact, even if you do, you probably have very few of them. Too few of them for this to actually be a particularly good approximation. So here are the problems. First of all, probably no appearances of H in the corpus. So here, when I use the word corpus, I mean data of all strings. And that are out in the real world that are using these tokens. Probably no appearances of H in your corpus, and even if the length of H is large, like this is. And two, even if H appears, it's probably not a good approximation. Because these might be zero as well, somehow. So this empirical count is probably not a good approximation of its probability of W being the next word given your history H. Right, so the somehow modeling, so I'm kind of introducing this to point out that modeling sort of next terms in a sequence is kind of a hard problem in general, just from kind of knowing everything that's been written out in the corpus from this point of view. But I do want to sort of introduce some ideas that are classical just to kind of give us some context around what the transformer is doing. So yeah, somehow what we're interested in but we're still interested in these sorts of conditional probabilities. So we're still interested in probability distributions on sequences of words. I'll say joint and conditional. On sequences in our sort of theoretical corpus. So this is really what something like a transformer architecture is trying to model, that it's trying to get at something like understanding these probability distributions. So you might, for example, the probability of a particular sentence so if you think of kind of the positions in the sentence as being random variables that can take on any value in the set of tokens, then some expression like this, you would hope in sort of a sufficiently large corpus to be something like the number of appearances of the string W1 through Wn divided by the total number of length n strings. So this is sort of for a sufficiently large, for an infinitely large corpus. I'm kind of saying things in a sort of vague way, mostly because I'm just trying to introduce ideas.
Wait, why do they need the infinitely large?
I mean, because this won't be a good approximation. This won't be a good approximation unless you've sort of considered all possibilities somehow, in some sense. Okay. So maybe, since I'm not actually saying very much that has that much content right now, let me just switch gears and say that these ideas lend themselves to kind of so always what you're trying to do is kind of model this probability distribution on the next word, given some history or some context. And the idea is that, especially if you're going to create some model that's going to try to do this, that actually is going to work in practice, you're going to have to somehow limit your context length, your history length. Okay, so there's a sort of simplifying idea. So I guess the before I say that, maybe I'll just say one more thing. Which is that if you wanted to actually compute this joint distribution, you would be able to if you, so there's this, you could think of this as like a chain rule on joint conditional distributions. But, so for example, if you wanted to compute the probability of this length 2 string, this is just the probability that the first element of the string is W1 times the conditional probability of W2, conditional of W1. So if you do this for like a length n string, you get this so-called chain rule. So if you iterate this idea, you would be able to compute this joint density from all these conditional densities, this string of conditional not densities, conditional probabilities.
What does the notation 1i?
1 to k, yeah. It's like a Pythonization of. It's like. Okay. So the point is that these get hard to compute or hard to estimate as these context lengths get long. So the simplifying idea assumption, which will appear in what we're going to talk about in lecture today about transformers. Is to approximate the history. We're putting an upper bound on the context length. So you're sort of making some kind of simplifying assumption that is maybe not great, but if you really want to compute something like the probability of this being the next word, or sorry, the next token in a string of length n minus 1, instead, don't look all the way back to the beginning, just look a certain way back. So this should be something like close to the probability of Wn conditional on so this computing these probabilities using counts from the corpus in the sort of empirical counts from the corpus is the subject of what's called n-gram statistics or n-gram probability distributions. So this is called the n-gram approximation. For this true conditional probability that you're interested in. And so you can kind of replace this with just conditional probabilities that you can estimate with counts in your corpus, where you just look a certain distance back. So 2 gram statistics, just look one element back. So they're predicting the next word just from counts of, you know, previous word and then the next word. Okay. Okay, so this again is sort of context for what I'm going to say next. So maybe this just kind of motivates a language model. With the maximum context length. To predict the next token by somehow estimating these conditional probabilities on tokens given histories of context length less than or equal to this n. So now n for the rest of the lecture today will be what I'm calling the context length. By maximizing this conditional probability over these tokens in your set of tokens for each fixed h of length at most n. Okay, so that's what transformers are doing. Okay, so let me now just get started describing the transformer. And as I do, I'm going to try to write down some explicit numbers which describe the sort of dimensions of the spaces that you're using for, say, GPT-3. So as we said, the inputs to a transformer should be sequences in some set of tokens. T, a set of tokens. And we may as well think of them as words, although that's not exactly right. Of length n. This is the context or history length. So the input to the model is just a sequence of these tokens. And so let me kind of draw we have this token sequence. And each element of this token sequence is now embedded. There's an embedding layer. That. So each token is embedded into some space, which at least in some of my references, it's called the residual stream. Try to write down some ballpark numbers as well. And I'm going to try to keep them on the board. I don't know how to do this in a way that doesn't take up a lot of real estate on the board, but I'll just do it over here. So for GPT-3, The size of the set of tokens, say for the English language, is about 50,000. The dimension of the residual stream, so I'm calling this D sub R, is about 20,000. No, 12,000. Specifically, it's 12,288. Context size is about 2,048. Context length. So it can only look 2,048 tokens back as it makes its prediction. Okay, so here's some ballpark numbers. So you have this residual stream. So somehow already, you have each of these individual tokens, and already you're kind of making some sort of compression to stick them into the residual stream. They're not each going to get a basis element in the residual stream. Okay. And then you have so-called attention blocks. Actually, let me describe what are called residual blocks, which have a bunch of what are called attention heads that are run in parallel. So I'll describe those in a second. But a residual block is an attention block followed by what we've been talking about already for a long time in this class, basically a ReLU neural network, also called a multi-layer perceptron. So you have an attention block which looks like a bunch of what are called attention heads. If you know about convolutional neural networks, these are like the filters in the convolutional neural network. They sort of run in parallel, and each one has its own data or parameters associated to it. But I just want to give you kind of a large scale view of it first. And then you have one of these MLPs. So this looks like what we've been talking about a lot already in class. Okay, and then you repeat this a certain number of times. So you have a bunch of residual blocks. So always in between, you're kind of mapping, you're always mapping through this residual stream. So in between, so after the embedding, you're in the residual stream, you have an attention block, and then you're back in the residual stream. And then you have an MLP, which could have, I don't even know typically how many layers they have, but you have something that looks like what we've been talking about. And then again, you're back in the residual stream. And then you have a number of residual blocks like this. And then at the end, you do an unembedding. Followed by a softmax. Okay. So something that I should have said at first that I didn't is okay. We have this set of tokens. The first thing that we do to even get started is represent each of those tokens by a basis vector in a space of dimension, the size of the set of tokens. So let me just say that now. to vectors before embedding. So called one-hot encoder. So essentially what you do is you list the collection of tokens. You fix some ordering on the set of tokens. So fix some ordering on the tokens in T. So it's something like T is a set where everything has now been ordered. And the length of it is the size of the set. And then you associate to each of these just the corresponding standard basis vector in so like E1 is just 1. E2 is so zeros, but a 1 in the ith position. And the idea is that this is sort of supposed to represent that this vector is this with probability 1 and is the other ones with probability 0. That's why this one-hot encoding kind of makes sense from the point of view of doing this. Okay, so there's this sort of pre-step where we've represented the tokens as these one-hot embeddings in this very high dimensional space. And then we're going to embed these into this residual stream, which is lower dimensional. Any questions so far? So I haven't told you anything about what these attention blocks are. We know a little bit about what MLPs are. And I haven't said much about the embedding map and the unembedding map yet. But just large scale, this is what's happening. Okay, let me, so now let me start, as I start to dig into what's going on here. Let me start by talking about the embedding and unembedding maps. Because somehow, you have all this interesting stuff happening in the middle, but actually there's already quite a bit that's interesting just in the embedding and the unembedding. So I want to talk about that for a little while first. So I'm gonna So you're thinking of these embedding and unembedding maps as finding a nice way of representing these tokens inside some high dimensional space, but it's not as high dimensional as like the number of tokens. It's slightly less. And what's interesting is that these maps are just linear maps. So each input to the transformer is a length and sequence of one-hot vectors. So, and it's encoded as realized as a each column of a matrix is one of these one-hot vectors. And then you have n of them, that's the context length. So it looks something like this. And then you have this embedding map. And I claim it's just a linear map. So let's represent it by a matrix, WE. I'm sorry. This maps from. This is a PR by T. And its columns are just the images of all the tokens in this embedding space. Because when you multiply this by some one hot vector, it just picks out that corresponding column. Okay, so the ith column is the image of WI in this residual stream, this embedding space. And now, of course, if you have a string, or sorry, a sequence of these columns, you multiply by this matrix on the left, it's just going to turn each of those individually into their images. Okay. So it's just kind of a compact way of doing that calculation. Okay. And the unembedding map is mapping. So elements of this residual stream, vectors in this residual stream, back to, well, kind of linear combinations of these one hot vectors. And what we're supposed to be imagining is that in the middle, the transformer has basically altered each of these embeddings in a way that takes into account the context. So that's the heuristic. That's what we're supposed to imagine. You embed at the beginning. So now you have the images of all of these. You have the images of all of these tokens in this embedding space. But then the attention blocks and the MLPs are somehow altering those images in some way that incorporate the context. So this is the story that people tell about what transformers do, although they don't actually understand really how that works. But that's the story that is told, and I think it's a helpful story. So, the way that I'd like to kind of motivate understanding that helpful story is thinking about what would happen if you didn't have any attention blocks or MLP blocks at all. You just had the embedding and the unembedding. Then what should this be doing? So let's think a little bit about that.
And if you're going to explain this later, that's fine. But these two maps, are you claiming, first of all, like, are you claiming that you said the first one is going to be linear? Is the last one going to be linear?
It's also linear. Yeah. Both of them are linear maps.
Are you claiming they have a relationship to one another, or not particularly yet? I mean,
They do have a yes.
Yes,
I'm going to tell you in a second what relationship they should sort of have to each other. If the training has gone well, what relationship they should have to each other. That's actually what I want to see.
Okay, and then I guess maybe the affine or something. Were you claiming that the image of the that map is onto
like probability vectors?
Sum to one?
No, we have to do an extra step. Yeah, thank you for that.
Okay.
Yeah.
All right.
Yeah. So
it's just some affine linear map.
actually, it's just linear.
Or
It's just linear, straight old linear. Yeah, but yeah. So in that kind of cartoon that I drew of the transformer at the beginning, you had this unembedding map, but then you also follow at the end with a softmax layer, and I'll say a little bit more about that in a second. Okay. So yeah, the outputs of these are sometimes called logits. So these are sort of the inputs to a softmax layer. I actually did want to point one thing out, which is not 100% clear from the setup that I've described so far, but which I think is actually an important thing to point out, which is that actually this unembedding map, strangely, even though you input a whole sequence, by the time you get to the unembedding, it's only looking at the image of the last element of the sequence. So somehow, you've got this whole sequence, this context, and that all gets embedded in here. And then you run a bunch of these fancy layers of attention and MLPs. But then when you do the unembedding, actually, and each of these embeddings somehow gets moved around by all that attention and MLP business. But for this unembedding, you only look at the image of this last guy. And that's the map.
In your first diagram, you had the embedding map going to R to the DR, but should it go to R to the DR times N?
Yes, well, so it maps
I mean,
those matrices to things that look like that, but the matrix itself is just a DR by
okay, so
T.
there's a matrix, but in terms of what's being computed,
Mhm.
after you do the embedding step, you have as you say, a matrix there.
Yeah, exactly. And the other thing that I should point out here is that the entries of these matrices are trainable parameters. Okay, so kind of behind the hood here, you're setting up an architecture, just like we did with the ReLU networks. You're setting up this architecture. You have a parameter space. You know what the dimensions of these matrices are. You know how many parameters you have, but you don't determine what they are until you've trained on some corpus. Okay, so let me just write that down. So the training data here. Training is length n strings in T, ordered sequences in T. So these would be the inputs, for your input output pairs, plus next token. So this is the output. This is it. So you have a bunch of length n strings and then the next token, length n string, next token. And that's what you're training on. And the entries of WE, WU are trainable parameters. And in fact, I may as well comment on what Melanie asked about now. This is probably a good time to say it. So, okay, so again, imagine you didn't have any attention blocks or MLP layers or anything. Really what you would have is, your set of tokens represented as one hot vectors in here. You have this embedding map, R, DR. And then you'd have an unembedding map back to this high dimensional one hot encoding space. And now you want to get some probability vectors out of this. So the standard thing to do is to apply what's called Softmax. And since I think I haven't talked about it in this class yet, let me go ahead and just say a few words about it now. So the idea is what you want to do is get a probability vector. So associate to each word or token in your set of tokens a probability that it appears next. And so what you want is to take some vector in R to the size of T and get a probability vector in R to the size of T. And the standard way to do this is to apply this function called Softmax, which I'll describe in case you haven't seen it before, although I'm sure many of you have. But I'll just note its properties and you'll see it right away. So this is a function from Rn to Rn for n. We'll take a string of real numbers. And it will just send it to e to the real number over the sum of the real numbers. So this is the map. And you can check that the important properties of this softmax function is that it preserves ordering. So because e to the is a monotonic function. If so, let me just write down a few things. So first of all, e to the xm over sum is always greater than or equal to 0, and that always greater than 0. If m is greater than n, then the corresponding coordinate will be greater as well. So it preserves this sort of ordering coordinates. And also it makes sure that things sum to 1. I shouldn't have used n. R. You see what I mean? The sum of these is equal to 1.
X and is bigger than 6 R.
Yeah, that's what I meant. Yeah. Yes. So it's preserving ordering. And if you take the sum, these. So this gives you probability vectors. So you get probability vectors out. But to be honest, I haven't explored that much how, it kind of distorts the, yeah, I've always kind of wanted to explore how it's kind of, yeah, distorting things. I guess if something gets a little bit bigger than something else, then it's going to be a lot higher probability because of the way the exponential works. So that's something to kind of keep in mind about softmax. All right, so let me just spend a little bit of time talking about this. What happens when you don't have any attention or MLP layers at all? Just what's going on here for like a well-trained transformer with no attention or MLP layers. And it's just coming from the fact that these embedding and unembedding maps are linear. So. Without any attention. Or NLP blocks. Transformer looks very simple. It's just what I put down. And in fact, so because of the thing that I said and I didn't write down, that somehow this unembedding map only looks at the last element of the string. Really, you don't actually need the whole string, you just need that last element. So the only, my claim is that the only place where you use all the elements of the string is in the attention blocks in the MLP layers. The unembedding map never looks at the previous elements of the string. So this looks like this. Just want to note, this is a linear map, and this is a linear map. And DR is less than T. So yeah, think like maybe a third fewer dimension. It's about the same order of magnitude, but it's smaller. Maybe I won't put 2 less than, so I'll just put 1. Okay. And I'll say also only looks at last element. So WE of XIN in the embedded context. So if you've looked at any of the sort of basic ML architectures, you'll recognize this. This is a setup that's very much like an autoencoder. So you have this bottleneck dimension. You're forcing your representation to be smaller and then bigger again. So you're doing some kind of projection than a re-embedding. So this looks like, and in fact, it's not, usually when you're talking about autoencoders, like neural network autoencoders, these aren't linear maps. These are more interesting nonlinear maps, like ReLU layers, or maybe a sequence of ReLU layers, for example. But this is just a flat out linear autoencoder. So this looks like a linear autoencoder. But trained to predict the next word from the last word of the context. So after training, if you've done your training well, it should predict the next word from just the previous word. So trained to predict next word just from the last word of the context. So in other words, the way that this would be said is that the ideal behavior of an attention and MLP-free transformer is to model bigram statistics. So n equals 2 n-gram statistics. So it's just looking one token back. So the ideal behavior is to model bigram statistics. This is not the way that I've been using n here. I guess n equals 1. So the probability distribution that you would want such an attention MLP transformer to model is the probabilities of the next word for 2-word sequences. In 2-word sequences. So somehow what it should be doing so if you look at, for example, let me just break down what this looks like in terms of linear algebra. So if you look at applying the embedding and then the unembedding to a 1-hot vector, this is the ith column of this product. Okay. And now what you're wanting is that when you take the dot product of that with the jth, the jth 1-hot vector, okay, so let me actually hold on a second. Let's say a little bit more before I write that down. So one that for all words WI in your separate tokens. So this has associated 1-hot vector VI. If you take if you embed it and then unembed it, so this is now the ith column of this matrix product. And then you take the dot product with EJ. You want this to be maximized for the J that has the highest probability. Right, so okay. All W. So in other words, the largest entry in this column should be the token that has the greatest chance of being next. Or WJ, greatest probability that probability WJ given WI. And in fact, you kind of want them to be ordered in the order that so in other words, right. So even better would be if you take the softmax of this the ith column of this matrix, embedding followed by unembedding. So this is the ith column. So this should be some probability vector. And you really want this to be close to probability that, say, W1 given Wi. And so it really should look very close to this probability distribution. This is, I guess, T given Wi. So the columns of this matrix are the logits of this, this bigram probability distribution, or should be after training. That's the ideal behavior. So you're actually getting a lot of information actually from this embedding, unembedding matrix. It really should model this bigram statistics. That's what the ideal behavior would be. Is this clear what I'm saying? Yeah, so somehow like looking at the columns of this product gives you, should give you information, even before you start looking at attention and MLP layers. Any questions about that before I go on? Okay. So the last thing I'm going to say, I'm not going to tell you yet how to compute attention for attention blocks. Instead, I'm going to tell you kind of roughly speaking what they're trying to do. So we already kind of know what MLPs are. The last thing that we need to do is talk about attention. The attention layer is some parallel. So in the sense that each attention head has its own trainable parameters. And all the computations can be done in parallel. They don't really depend on each other at all. So parallel attention heads. You should think of it as a stack of attention heads, like sheets of paper. And the heuristic is that each of these heads is asking represents some question that each token is asking the previous tokens. And depending on the size of the answer of the previous token, in the sense of, you know, greater in R, you will now attend to that previous token as you're answering this question. In practice, I don't actually know the extent to which people have looked at attention heads and figured out what question that attention head was asking. But practically speaking, for each head, you have you can look at which tokens have the greatest attention values for the previous tokens. Okay, so I haven't really said enough for you to understand what that means, but the sort of example of some kind of question that an attention head might ask is, I'm a noun, are there any adjectives in front of me? Something like that.
There's a new paper that came out that looks exactly.
Oh, really?
It's from last week. Yeah.
Oh, great.
Yeah. I can look up the name and Terry.
Yeah, I would love to see that. Thank you. Yeah. Okay, so you have these parallel attention heads, and the idea is that each one of them is supposed to be responsible for asking some question or some query of the previous tokens in the head. So the idea is that, you know, what's the input to one of these heads? Well, it's just something like an embedded sequence of one hot encoded tokens. You know, so you have some, if your context is size n, then you have a bunch of these tokens that have been embedded in this residual space, and these are now the columns of this vector. This is the input to the head. And the job of the attention head is to produce two pieces of information. So the first piece of information, so the attention head produces two mathematical objects. The first is what I just described, an attention pattern. An attention pattern, and I'll describe next time, I'll get into the details of what it's doing when it computes this attention pattern. But at the end of the day, what this looks like is just an upper triangular matrix. So there are zeros down here. The columns are all probability vectors. This is a column-wise stochastic matrix. And it's n by n. Okay. And why is it upper triangular? Well, it's because tokens can only attend to tokens that are upstream of it. So you impose this because the idea is that you can't use future outputs to predict anything. You can only use what you've seen already in the history. So somehow each token is trying to understand how to attend to previous tokens in the context. It's not going to attend to tokens ahead of it. Okay, so these are probability vectors. It's upper triangular. Tokens can only use upstream information. They can't use the future.
So when you said, as an example, like, I'm a noun, are there any adjectives ahead of me?
Oh.
Ahead, you meant
I meant behind me, yeah.
but previously.
Previously to me, yeah. And the last thing I'll say is that the other output of an attention head is a low rank matrix. And the way that you guarantee that it's a low rank matrix is the same way that you somehow always in this subject guarantee that you have a low rank matrix. You multiply two matrices that are hot, that you construct a bottleneck layer. So you realize the matrix is a product of two matrices that are skinny. So this is sometimes called the output value matrix. And it's realized as the product of an output matrix and a value matrix. Where just as before, you're factoring through a low dimensional space. So I'm going to set this up again. So you have the residual stream. Now you have some lower dimensional space. I'll call it the value space, maybe. And in GPT-3, DV is 128. So it's actually quite a lot lower. So this is. So what you're doing, okay, so again, I'm not going to have time to explain I just want to set up the sort of structure here. But essentially what's going to be happening with these attention blocks and this low rank matrix is that you are using you're using the attention to decide. So for each of the tokens in your set of tokens, you're constructing some low dimensional projection of it. This like much lower dimensional projection. And then a re-embedding. And the attention pattern is going to tell you exactly how to do the linear combination of the outputs of this. And what that does, at least heuristically, is change the values. So you're going to end up adding that back into these embeddings of the original tokens. And that shifts the embeddings in this embedding space in a way that's weighted by these outputs values, the output of this output value matrix. So what's happening is that each attention block is figuring out first how each token is going to attend to the previous tokens. That's going to give some kind of linear combination, which you're going to apply to the output of this low, this projection embedding. And you're going to add that back into each of these vectors. And the idea is that it's going to shift the vector in this embedding space so that its meaning has somehow shifted in some way that has taken the previous tokens into account. But you can see this is like a very, very like rudimentary thing from the point of view of like linear algebra. You're like literally, you're just like projecting things down to low dimensional spaces and mapping them back up in some way. Again, the parameters of these are all getting learned. And the attention is also there's some parameters in there that are getting learned. So next time I will finish telling you about how these attention patterns are computed. And then we'll kind of go from there.